So thanks for inviting me, and I'm not going to be talking about Python, even though I have used Python in my life. I'm a physicist, and it's pretty much impossible to avoid it if you do physics for living at some point. But my talk is actually going to be on a completely different topic, so you can relax and get ready for the weekend. I'm going to be talking about lasers. And lasers are cool, we all know that. We also have seen Star Wars and all those things, but that's also not what I'm going to be talking about. Basically, lasers are extremely applicable and extremely useful. And it's not really a coincidence that the Royal Society in the United Kingdom a few years back pronounced the laser to be the most important invention of the 20th century. I like to say this because now we're talking about the 20th century, which is like we got all the semiconductors, we landed on the moon, and scrap all that. It's lasers. How cool is that, right? And the reason why they said that, they didn't say it for nothing. First of all, they wanted to send a real message to David Cameron, who was just scrapping some science funding that, we don't need basic science. I said, well, actually, we wouldn't have all these things if we hadn't had basic science funding back in the 50s, and 10 years later, we ended up with lasers. And the reason they were able to justify this message is because this invention went into pretty much every single human activity that we can think of. It's gone into entertainment, medicine, manufacturing, information technology. We wouldn't have all this fast internet and these cool messaging capabilities or whatever you're doing for a living if we hadn't had optical communications. And that's all done with lasers. There are just way too many applications that we can think of. But what really is a laser? So I imagine a lightsaber when someone says a laser. I don't know what you do, but usually it's something like a beam. They never look like that, by the way. Someone must have put a lot of nasty, not very clean stuff in their lab in order to make those lasers and take that picture. And we usually don't do that. Lasers are light. We all probably guessed that. But they're a very special kind of light. And I remember when I first studied laser physics, they almost made us memorize these few characteristics that I have in the bullet points up here. The most important one probably, lasers come in one single color. Well, when I say one single color, we usually say monochromatic because it sounds much cooler when a physicist uses these really awesome terms that no one else understands. It basically means one color, really. It's not quite like that. I'll tell you a little bit about that later. But essentially, we have this very special monochromatic light. But again, if you wake up in your bed every morning and you have this very annoying alarm clock on your bedside table, that also has a monochromatic light source. It's usually some sort of red LED. And the main difference between those two sources, which are both monochromatic, is this thing we call coherence. I like to just say the light waves are aligned, which is also a very extremely important characteristic of a laser. So coherent monochromatic, we can make them polarized. That means they're also kind of coherent in space when they propagate. They allow divergence. We all know it's a beam. If I had a laser pointer, which I forgot to bring here, I would be able to show you that I have a little dot on the wall or something. So they do travel in one single line, which is also why you don't see the cool lightsaber or anything. Because unless something is in the way to scatter your light, you can't actually see it because it's not reaching your eye. And that's also a very important characteristic of a laser. And the high intensity, this is kind of why I'm here and why I do my research. You can amplify light, and it's kind of already in the name of a laser because it says laser is a shortcut for light amplification by stimulated emission of radiation. So we love these acronyms. It sounds much cooler when you say laser than all of that stuff. But it's all in that name. It's light, its emission is stimulated, and is massively amplified. And I'll try to explain a little bit about that. This is very elementary atomic physics. Those little blue dots or balls are electrons, and as we all know, electrons are always blue, and that's a very important part of this talk. We've had decades of discussions about this. Well, so normally you have some sort of energy levels in an atom. We all know what atoms are, little bricks that make up all the matter in the universe. Around these atoms, they actually don't go around like that, but we like to draw it like this. We have these energy levels that the electrons can populate. And what I will tell you now, a very important piece of information. Laser always is based on minimum 3 energy levels. And the good reason for that is because you first need to excite these electrons. They have to go up there. But they don't like to stay on the level you normally excite them to. They have to go and sit down somewhere else. So I like to check audience. It's very easy to use this analogy. You go for a trip. You want to go biking with your friends, but first, before your friend actually visits you, you're just kind of sitting in your sofa. So that's your base level. That's your ground state. You don't really want to use any energy. Then someone excites you, go on a biking trip. They take you to the next upper level. You go there for a little while, and about 1 or 2 kilometers later, you see a pop. So we all know what happens at that point. You start hanging out in the pop. After a few beers, you have this thing called the population inversion. That's, again, a very important term from physics. That just means normally electrons would like to be sitting down there. Instead of the sofa, they're all hanging out in the pop. And for a while, they're sitting there. And this is why they have these different quantum probabilities that they will live in these 2 different states. And at some point, something stimulates them. They all fall down at the same time. And when things fall down in energy levels, they release energy, and energy is light, or electromagnetic radiation. That's where the word radiation comes in. So it actually works a little bit like that. And the stimulated, it means that actually the one thing that can stimulate all these electrons to do this is a photon, a light particle that will come in. So really, what it looks like, you need to have an active medium. So the first laser was the ruby. There are good reasons why all these really pretty gemstones were the first lasers. They have the color, this prettiness that we call them gemstones for. That's actually the same kind of optical properties that we require in order for them to lace. We use that word, to lace, actually. That's also quite cool. Now, we need to obviously, as I was saying, explaining, electrons they need some excitement, they need to get up to the higher energy level. You have to pump it with energy. So you usually use different types of flash lamps or light sources. You can use other lasers, or just electricity. Laser pointers or diodes, they just excited by electricity directly. And the next most important part is the resonator. So you have a cavity with 2 mirrors on either side, and your light will just bounce there and back. And every time it bounces, it will collect a few more of these photons, and you'll end up with a little bit of an avalanche reaction. So every time you get excited, more and more atoms will excite more and more electrons until you saturate the medium. And at that one point, you either burn it, which does happen, or you switch it and you let the light out, and that's where your laser pulse comes from. But I'm mentioning the burning part for a very good reason. So in the 60s, when they first invented lasers, they were happily amplifying up and up and up, exciting the media more and more until they started burning holes in them. So you don't want to burn a hole in your ruby. Even less, you want to produce a laser which no longer lasers. But you want to have more and more radiation out of your laser. You want to have the more intense lasers because it can do much cooler stuff with bigger lasers, obviously. And so how do you get about this thing? There was this very famous, very clever man, Jerome Roux, who was a French physicist at the time. He was working in the United States, who came up with this beautiful technology. So now you forget everything I told you about monochromatic light from lasers. They are not monochromatic. This is what I always had the feeling, they teach you some new physics, and then you go to the next level, and they tell you, forget all your old physics. You go from high school to university. Then you get to your PhD, like, forget all your university physics. This is completely new physics. So I'm telling you exactly the same thing. Forget about monochromatic lasers. They actually have colors. And yes, we have this rather narrow, or it can be a relatively broad range of wavelengths, which are in our pulses. And you can do essentially the same kind of thing as you do with a rainbow. You can use a grating that will split your pulse in space. But in space, that can also mean in time if you define your beam path in such a way that different colors will arrive on optical elements at different times. And that's how you can basically get about this whole burning hole in the mirror problem or in the medium. You basically, The reason why something will burn is because it overheats, and it overheats because there's too much energy there at the time. If you stretch it out in time, you no longer have too much energy at a given point, so you can keep on amplifying until you get to the threshold of burning again, which is what we do. We always go to the very limits, and then you use another grating and you put it back together, you end up with this beautiful big pulse. This is exactly how these short pulse lasers and all that stuff I work on is actually based on this. Without this invention in the 80s, we wouldn't actually be able to do all that very cool stuff that we do now with giant lasers. I'm going to be talking about those in a very short while. Okay? Wavelengths. No, what it means, you will have your grating at a specific angle. So you shine in your beam, and your grating will split angularly your different wavelengths, little components. And then you set up your beam path in such a way that the different colors will be traveling in a line, essentially. You split it into a bit of a line, just like the rainbow.
So the fiber will have different line? Or?
You can do it in a fiber too. In the very big lasers, we just let it propagate in vacuum. But yes, all it means, it's not different weights of fibers, it's just spatially, they're separated. Imagine I would give you a rope, which is the same length, and I will split it like this, but I would cup the view sideways. So you can visualize it that way, for example. Anyways, I like this picture. So lasers are cool, but what you do with lasers is even cooler. And a lot of people don't realize that lasers can be used as giant accelerators. We all know about CERN and those things. I already heard that there was a talk about that. What if I told you that the same thing you can do in CERN in a kilometer, I can do in 3 centimeters with a laser? That's pretty awesome, right? So yes, we do that. It's not quite as controlled in the same way, so there's different applications. We don't actually compete. Well, sometimes we do. Sometimes. Not necessarily, but basically what we can do, we can accelerate electrons, protons, all sorts of particles. In fact, I was in a team that was the first one to make a strong neutron beam with lasers, and we do lots of different types of radiation, especially X-ray radiation. Of course, these things are extremely useful because you might have heard of how biologists use diffraction for figuring out structure of pathogens so they can make new vaccines. Well, they usually have to freeze these samples. They actually change the structure slightly, so that measurement itself becomes very inaccurate. They have to take it to massive synchrotron, which costs a lot of money, again, kilometers of accelerator, and they come up with something that they can use. We can do this with a relatively small laser on a femtosecond timescale without having to freeze these samples with the lasers. So it's a very big step forward. So this is why we love these applications. This is why we need to go to these bigger lasers, because only these very slightly bigger lasers, not the little laser pointers, can go and become things like particle accelerators on new X-ray sources. But the one application that really got me going when I first was choosing what to do for a living is laser fusion. You may have heard of how we need fusion for future energy and all those things. It's probably gone through media. Most of the people think of tokamaks, these big magnetic vessels that confine plasmas and produce sustainable reactions for, well, now they can do like a minute. No, actually, I think they quite made it to a minute. Anyway, we do something similar with the lasers. Essentially what it is, we have to create the same kind of reaction which is powering all of the stars, including our sun. This is the second most energetic reaction, or energy efficient reaction in the universe after annihilation. Annihilation, when you take particles and antiparticles and they just turn into pure energy. So all of your matter turns into energy. This is the second best we have. The entire universe you see, which is shining, apart from the moon, which is reflected light on some planets, all of that is fusion-based light. All of that energy, we exist because of this fusion. So why not create it on Earth too? Well, we kind of did. Bikini Atoll saw that and they didn't like it very much. I did work in Los Alamos in that exact group that set up that beautiful thing on Earth. That is not so great for a power station, but we can create similar type of device fusion device with lasers. So in a hydrogen bomb, this is done by nuclear loads put around a fusion pellet, which is deuterium and tritium, which is supposed to fuse, because you basically have to create these extreme conditions. Now we're talking millions of degrees, and high pressures, now solid density, so something which is more heavy, solid, dense than a lead brick, but it has millions of degrees, and it doesn't like to stay together like that. Just like the positive cores of the hydrogen isotopes don't like to fuse until you force them with a lot of energy to come together close enough to overcome the repulsive Coulomb potentials. So we do that with lasers. We have 3 different types of main technologies. They are not alone, but basically the first one is the indirect drive. That's basically a copy of the hydrogen bomb. You have a gold can. You irradiate it with, instead of the nuclear device, so you irradiate it with lasers. You produce a lot of X-rays through that extra heat, and that compresses a frozen deuterium and tritium pellet and forces it to compress and heat up. So basically something you can visualize as rocket propulsion. So when all this radiation comes onto the surface, it starts ablating the material of it, and it drives the rocket in. And that simultaneously compresses it and heats it up. There's a new technology which I like better myself. We can do it directly. Why not just shine the lasers directly onto the pellet? There are problems with that because obviously, how do you make it homogeneous? That's a little bit more challenging, but it actually has been done, and I've had great results. And the third one is a fast ignition. That's actually a pretty cool new idea, which hasn't quite lived up to its promise yet, but it's not completely off the table at this moment. Basically, the lasers that like to accelerate particles are the ones which are shorter pulses. The ones that like to compress things are long pulses. And when I say long, it's nanoseconds, so 10 to the negative 9 of a second. So that's not exactly long, but it's longer than 10 to the 15, which is the femtosecond, which accelerates a particle. So I live in slightly different time scales, just in case you were wondering. So you use the nanosecond laser to first compress, and then you bring in a short pulse laser which accelerates electrons or protons, which then heat the compressed fuel separately. And that was an idea to make it a little bit more efficient, but they haven't quite got it to work because the physics is really difficult. Now, there are really big lasers in the world. In fact, we only have these really big lasers because of fusion and because of nuclear weapons, because some really big governments have decided that they want to test these ideas the scientists have come up with. So this is I think it's currently still the biggest lasers and will for a while will be. It's the National Ignition Facility in California, in the Lawrence Livermore National Laboratory. And that little picture down there, that's 3 football fields. That's how big the laser hole is. And you can't make it any smaller. In fact, they already are forcing the lasers to go through the same laser rods 3 to 5 times. So, and after that, they just pump so much energy in it, they would just explode. So they can't reduce this any further. It's impossible to make it smaller. And the beams themselves are like close to a meter. They're like over half a meter in diameter because they're so intense, there's so much energy in them, you'll burn a hole through the mirror that's reflecting it. So it's a really freaking big thing. The vacuum chamber, that's the interaction chamber, has a guy standing in it. You could have like 3 stories in it, so 3 guys on top of each other. I touched it before it became radioactive, which does happen when you have a lot of energy hitting stuff. And that's actually where they filmed the latest Star Trek movie. I'm not sure if you remember the warp core, the Starship Enterprise. In fact, a lot of the guys in the red shirts in the back that probably exploded at the end of the movie were the scientists from the lab because they use them as stuffs and stuff. So it's pretty cool. So a lot of my friends are in that movie, and they're very proud of it. Because it is a fusion reaction, right? So we thought it was really fitting. So I thought the Hollywood finally did some real science. So yeah, they took it to this really big, that's the chamber over there. So in case you watch the movie again, remember those big beams? That's actually how the lasers get in, because they have to travel in a vacuum. So as we know it, when Americans build something big, the French go like, oh, no way, we're having something big too, right? So it didn't take that very long. So first the Frenchies waited until the Americans, solved all the problems, and then they built an exact same copy of that. And this is their football fields over there, probably different kind of football. But they're actually already functioning. I think maybe about a third of the beams. Now, there are going to be fewer beams. Now, the National Ignition Facility, NIF, has something 192 beams. Now, these guys are going to have over 200 beams, just over 2. But they're a little bit less energy. So they're about on par with one another. It's exactly the same idea. And of course, both facilities are run by the guys who have the nuclear weapons. Now, Americans went like, well, we have 2 anyway, so who cares? So this is Omega Laser. This is where I did all my doctoral work, and I continue working with them. This is the previous 2 are basically recreating the hydrogen bomb. These guys are actually the ones with the direct drive. So you may notice all of the beams are actually coming from all directions, not purely so they can get inside the can. That's the main difference between these 2 kinds of facilities. They actually build a short pulse laser too because they want to test fast ignition as well. And this is a really cool place to do real science. So we've been doing lots of basic science, laboratory astrophysics, those kind of things here too. And they're really professional. And the cool thing about them, and I have to say it on them, they're run by a nuclear submarine captain. So I come from a facility where we take all this European money and we come through this extremely inefficient bureaucratic management, and somehow we hope that we'll get some science done. The Americans went like, no, we actually need real efficiency. And who's more efficient than a captain in a nuclear submarine, right? And knows all the technical stuff. So they took one. And in fact, when I started that, they stood in a line and they essentially saluted each other in the morning. And it was like, all the systems operational, yes, aye, sir. And they're extremely efficient. I've never seen efficiency of this level, so they obviously are doing it right. The very opposite can be said about the Japanese, because that was a very confused place to work. But they actually do very great stuff, but I had no idea what was happening. So this is their lasers, so they attempt to do a little fusion device. It's smaller, it's really cool, very, very good, very good facility. But every time I came up with a new idea, and I'm like, oh, can you build this for me? And it's implied to say no in Japanese, or it's actually implied to say, no, I don't understand, can you explain it again? They go, hi, they run off, they come back, and they come up with something completely different. It's like, thanks, but I don't want this. What is it anyway? So it was really hard to do research in Japan, but we did that. It was kind of fun, and we came up with some really good things. And of course, the British, they also have nuclear weapons, so they have to have a big laser. In fact, they already have a second one. And this one is really cool. Some of my friends have recently, so anyway, AWE is Atomic Weapons Establishment, so they're really serious about the AWE. But if you actually look up just the acronym, it's like the best charitable place. They have all these activities for children. They support cancer research and all these things. They have extremely good PR until you separate, you find out what the acronym actually means, and then it sounds a little bit worse. In any case, they do really cool science, and it's mostly, again, combination of short pulse and long pulse lasers. They don't do actual fusion, it's not big enough, but they're very great for a lot of the basic science. And they have built this one with academic access, so UK researchers and their collaborators can get in for part of the time and do some very cool experiments. But it's not just that. I mean, facilities, we need a lot of, in order to do basic science, and this is kind of why I'm talking about all of this, we need a lot of smaller lasers around the world to do the basic science. And there are plenty in Europe, and they're actually building one of the biggest ones in Prague, or just outside Prague, right now. And I work for them. This is ELI Beamlines. They have, I'll tell you a little bit more about us in a minute. So this is what it looks like. We have all these different levels. Lasers will live in the middle floor, and all the cool stuff in physics always happens in the basement. I normally don't see the daylight, which makes sense because I work with lasers and they kind of get in the way, but it kind of sounds horrible when you say it. It's like, you're like a mole. Anyway, so this is what the different halls look like, and they will be doing lots of different kind of science. And that's actually very cool about this facility. It's very versatile. We do lots of very different things. So and also with lots of different lasers. So we have 4 main laser systems. L3 is one of the bigger ones that arrived yesterday from California. So actually the guys who have the biggest one, they built ours. So that's pretty good. So that's a good sign of quality. They know what they're doing. We're actually developing our own laser, L1 as well. That's a very special kilohertz system. That's very unusual. But we will also have L4, which will, the 10 petawatt, will be the most intense, the most powerful laser in the world. That's being built in Texas. And that one is pretty cool because you can actually split it. So we'll have 2 big compressors. That's where the last grating is going to be. Each one of them as big as a car for a train. So they're kind of smallish lasers. Not really. But so we will be able to split it into 3 different beams to do lots of different stuff. But briefly, just run through it. So one hole will be specializing in biology. So I told you about the structural studies, getting structure of materials and the pathogens, so you can understand get your new medicines and etc. One hole will be specializing in X-ray sources. I told you lasers can create secondary sources. So there'll be a betatron source, mostly for imaging purposes. You can take it any sample. Instead of taking it to synchrotron, you can take it here, and you can do your experiments with it. Again, lots of different applications will be done with also the L3 laser. Ion acceleration, again, one dedicated hole for that. That one is kind of cool because they also like to show that they're useful because they can cure cancer. A little bit far-fetched claim as it sounds, but actually these guys, you've probably heard of hadron therapy, proton therapy. You can irradiate cancer cells with hadrons or protons mostly, and they can kill that. But of course, if you do use normal reactor, that's actually not very good for you because that can kill all the tissue around it. But with lasers, because lasers are directional, your beams are directional too, and you don't have to go to an accelerator facility. You can do it on a laser. So they have a pretty good case for this research too. You can use electrons. Again, electrons just like X-rays are very good, useful probes. But to save the last and coolest thing, we also have a playground for physicists, and it looks like this. This is where you can do anything. It's just like, you go to your playground and you suddenly see the sandbox, and that's unlimited realm of possibilities. So we'll take all of the lasers, including the biggest one, and we can design whatever we want. We accelerate particles, and we're plasma physicists. I'm a plasma physicist. And plasma is basically the 4th state of matter. This is why the stars shine. They are the ones the balls of plasma. We're now talking about something is ionized gas. There's so much energy in it that has to radiate, but it can be all sorts of different kind of things. It can be flames, or it can be inside the big planets. And what I do is actually study the very dense state of plasmas, so-called one-dense matter, which translates into Czech in very problematic ways. You can only imagine, but so I don't translate it usually. And it's basically a transient state between the classical plasmas, that beautiful stuff, which is very elegant and nice and easy to understand, and the condensed matter, which is, again, quite nice, elegant physics and mathematics, and all the horrible mess in between with a lot of statistics and unbearable nonsense is what I love to study. So one-dense matter is in the middle. It actually is a transient state in fusion too, so a lot of my research is closely related to fusion because I tell them if their pellets are going to be compressing well enough so they can actually get to the fusion reaction conditions. Or I can tell them how a dynamo of a big planet like a Jupiter works, because I can tell them when ionized hydrogen atoms under these extreme states will become conductive, so you can get a magnetic field going. And the way I do it, I actually have to use lasers, and I have to create X-rays and particles in order to probe this matter. So I have been now developing very new types of probes, mostly with these femtosecond lasers, to tell me, so I can X-ray this matter. So I need one laser to will create these dense hot states, and another couple of lasers that will then study them, like with those X-rays. And they will tell me how dense, how hot, what sort of structure, and everything is going inside of those is. And this is why places like ELI is perfect for me, because I do have that combination. I do have that playground where I can do all these cool things. And by the way, we do patents and new things on the side, because we all know that plasma TV is a byproduct of fusion research, right? In case you didn't know that, that's what it is. So that's why we need basic science, and thank you.
Well-deserved applause.
Thank you.
Okay, so let's get to the questions.
Oh, wow.
Yeah, we have lots of them. So, why can I see the beam when pointing green laser pointer at the night sky, but not the red one?
That's a good physics question. So that could be two reasons for it. Light scatters, right? So the reason why we see blue sky being blue is not because the sun shines blue, but because the blue scatters the best. So we see most of that. So it might also be related to the fact that the short wavelengths, which is the green light, is easier to scatter in the atmosphere with all the water particles. Second very good reason why green is much easier to see, even with the same amount of scattering, is because our eyes are actually more sensitive to it. That's the first wavelength band that our eye developed to see. And after that, we started expanding from that. Possibly because everything around us is kind of green, and green is really cool, but that is why we see green very well, which is actually kind of confusing. The most dangerous laser is usually the red ones, or because they look like they're very dim, they're not very intense, but actually they're much more intense than the green ones, but we just don't see them as bright. We don't have a very linear detector up here.
Cool. Nice. So, does laser fusion produce more energy than it consumes? How does it compare with tokamak in terms of energy consumption, production?
Laser fusion, inertial confinement fusion, not the laser one, but the hydrogen bomb is the only one that actually really produced more energy than, and we saw it, and it was not that pretty. No, so far they only had a so-called scientific breakthrough. They basically twisted the definitions of the break-even conditions until they came up with something that looked good. They were hoping to do that with NIF. They found out the physics was more complicated than that. In fact, my own thesis showed that they should not be able to do that with the current models, but that doesn't mean that it will not work in the future. We just need to understand the dense states of plasma better. So right now, fusion does not produce more energy than it consumes, and it will, for a long time, will not do so. And it's worse than tokamaks, but it's also worse than tokamaks for other reasons, because, for example, since tokamaks cannot be used as weapons, they have a lot more support in research. And so a lot more effort has been put, scientific research, basic science effort has been put in that field. So if there's an fusion reactor that will be first, it will probably be a tokamak.
Cool. What would happen if the beam was just shot outside of the building into open air? Can we build a death ray like that?
It would probably just... Okay, I say it like that. So when I was a student and I started playing in the lab first, it was really good fun to go and focus the laser in air, because it'll go like, and there's a little flame coming up, and if you put a paper in it, it actually catches fire, and it's really quite awesome. Don't do that at home. So probably the same kind of thing would happen. Actually, lasers, this is why we have to transport them under vacuum, because as soon as any of the kind of energy intensity hits air, it will just start going like, there will be lots of light and not much happening, because you start producing plasma right away. But it's actually not a good kind of plasma, and it will not be a death ray because it's not focused, and it will not do very much because it will just break air. That's all it is. So it would be quite a useless death ray. If I was going to build a death ray, which I actually do for a living, I would transport it under vacuum until the very last moment, and then when it focuses, that's when I blast the death ray out of it. So yes, that's the better way to do it.
Thank you. Let's not try that, okay?
Well, unless you want to work for us, in which case you get paid to do that.
Yeah, but you have the playground. Okay, so how many laser pointers do you own?
Not a single one. I actually don't have a laser pointer. And the ones I like to do my demonstrations with, I always borrow from the lab. And I'm really weird that way. All the kids are around are like, oh, I show you my cool laser. I was like, okay. I mean, okay, yes, my husband does Python programming for fun in the evenings, but then he's weird, right? We don't normally bring work home. That's just not okay. So no, but I think I actually might buy one at some point, but it will have to be a very cool one.
Okay, nice. So, do you ever catch yourself saying pew 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 at work when using them?
All the time. And it's for different reasons, right? I mean, like a single shot on a big laser like this can cost $1 million. I go like, this better work. Because otherwise I'm in trouble, and it does happen. So yeah, it can be nerve-wracking. Yay!
Okay. How much power do these lasers use? What did a PW on the L4 laser? A petawatt?
Yeah.
What's that?
So a the L4 is going to be 10 petawatt. The biggest lasers right now in terms of power are about 4 petawatt. Well, at least the Chinese claim that. No one believes them, but apparently they measured it. It's a lunchtime conversation at this point. Power is a misleading term because when you come and visit ELI, and you should, they have this long corridor when they show the laser holes, which are soon going to be filling up. They show these big bars, these kind of lines along this corridor, which is supposed to demonstrate how much power each of the laser systems has. And they compare it to nuclear power stations. So Temelín, our biggest nuclear power station, is about this long on that line. Then all of the nuclear power stations in the world put together are about this big in terms of power output. The single shot in one of these L4 lasers is 35 kilometers long line. Well, they actually didn't draw the whole thing. They just said it's 35 more kilometers that way. Thing is, it's misleading because it's actually not that much energy. It's a kilojoule of an energy, right? How much is that in energy? 1 joule is you take a bag of flour and you lift it by 1 meter. If you do it 1,000 times, this is a kilojoule. You'll be tired, but you don't compete with a nuclear power station exactly, do you? But imagine you take this much energy and compress it to 10 to the negative 15 of seconds. Because power is energy versus time over time. And that's kind of where this misleading thing comes in. So people always like to ask me, how many power stations do you need to power your lasers? I'm like, I just need a couple of capacitors. That's all. That's okay. And a normal power line. So it's all about the time duration of the pulse.
Nice. So the last question, in the 50s, what did the researchers of lasers think the applications of them might be?
Nothing. Absolutely nothing. Actually, I had this is the best part. So I was studying for my undergraduate at a place where the first quantum optics professionals actually were. So the first guys who went so quantum optics is what has given birth to lasers. And quantum optics is if you just see the mathematics, it's a pure masturbation for the fun of it. There's nothing, absolutely no reason why anyone would want to do that for any application whatsoever. They only did it because I was like, well, it would be really cool to make these potentials oscillate and see what sort of maths comes out of it. That's the only reason they did that. And 10 years later, a company was actually building the first maser and a laser straight after that. So that's why this was such a great example of basic science, because they only did it out of curiosity, and they didn't think it was good for anything.
That is cool. We have one last question because it's almost 6 o'clock, so we need to go and listen to the lightning talks.
Yeah, I know.
Yep.
Hi.
Hi. Can you just tell us if lasers can somehow be used for quantum computers or something with computation?
Yes, actually, yes, absolutely. Quantum computers is what I did during my PhD too, on the periphery. The same kind of atomic physics and now the quantum optics is the same theoretical and practical basis as for lasers as for quantum computers. And the reason why these two are directly related is not only the atomic physics part of it, because quantum computer works on the basis that you have two energy levels in an atom, and that's your 0 and 1. And you flip between them, you have to build some sort of logic gate, which is, by the way, one of my professors from Oxford is still waiting for his Nobel Prize because he came up with a logic gate based on that. And you will need a laser that will be exciting the electron between the two. And in fact, you need a laser of very specific wavelengths. So you isolate only those two energy levels in an atom which has hundreds or thousands of energy levels. So
you're using the laser to build the qubit out of electrons?
Absolutely. So it's actually very complicated. There are different methods. Some guys in Cambridge, they try to use crystal lattices. That's to actually try to build a hard drive out of that. The more mainstream thing is to basically laser cool atoms and bring them to very, very cold state, which will help them to essentially not oscillate, because if you have any temperature, if you essentially start exciting electrons all over the place, you want to keep them somewhere cold. So they use these cold atoms, and that's actually done through laser cooling as well. So you take 6 laser beams in different directions, and it basically forces the atoms into complete stillness through the basic light pressure. And because you have 6 degrees of freedom for any motion of a particle, you use these precisely timed laser beams to do that. So they keep them in these cool states, they can laser cool them, and then they can use another laser to basically flip them between your energy levels that you define through some complicated atomic physics. And there's a lot of maths and complicated stuff behind it, but the core, basically the same guys that were just going in the 50s, this would be really cool to do, that comes from the very basic equations. All of these things then comes back together as for that application. So lasers and atomic physics and quantum optics is all part of this thing. And I think actually some companies are already starting to look into it. IBM and the others, I think even Google had some funding on this. So perhaps quantum computing will happen at some point. I think they have a byte now.
Yeah.
That's pretty impressive.
So how scalable is it? What's the state-of-the-art of the...
So how stable?
Scalable, like how many qubits?
Scalable.
How many qubits can build with it?
So that's okay. Now the problem is actually, So it's very hard to scale something from a byte when you need to have a vacuum chamber this big just to keep it going for 1 byte, right? That's why the guys from Cambridge are coming up with this way of using lattices, crystalline lattices. And they're trying to use that as a full hard drive because each one of those atoms is basically 1 qubit. So you can build up your memory or whatever from that. But they haven't really been able to isolate them properly. So that's just an alternative approach to cooling individual atoms. We're still on extremely basic physics side of development of that. I mean, fusion is probably more likely to happen than a quantum computer, I would say, at this point.
Okay. Yeah.